के आउँछ त यसमा मोटिभेसन हेल्प क्लोज नामै फरक
No, निस्क्यौ यतिर गयो ऊपर रिवाइभ हुन्छ हो नडराउ न यार माथि हिँड्न त कान्छ जान मलाई तिमी सिक्स कान्छ नै म पुसान्छु ल ग्राममा
Okay, Mozilla Firefox here. Good.
त्यता छ डाँडामा
आज हाम्रो के गर्छ म
सेक्सी जाऊ न तिमी यहाँ
रोड म्याप हेरौँ न त Yes, but योभन्दा अगाडि AI डेटा साइन्स यसमा कफका सबका
बम हानेर थोरी
all roadmaps AI and data scientist जान्नु पर्यो DevOps backend Python Go कहाँबाट सुरु गर्ने त यार Programming fundamentals. DevOps roadmap. Backend AI data scientist के हेर्दैन त
हो त्यही
यसमा पनि mathematics algebra calculus
कता आयो म त्यसको कसरी गइदिन्छु
statistic stat math Coursera introductions
nice
statistics Coursera नगरम AB testing Durdas
कौन छैन अर्को एनिमी छ हो त्यहाँ
test sensitivity ratio matrix के होला यो त के थाहा छैन स्टार्ट त्यसपछि बल्ल इकोमेट्रिक्स फन्डामेन्टल अफ के regression time series fitting distributions integral economic and ball coding algorithm Python explain data analysis ball EDA this is ball machine learning what the course processor machine learning mathematics course YouTube
गाडी छ भने ल्याउन त जाम काम छैन बस्यो
Number 3 as a
चलो तिमी छ
mathematics.
देसिल खायो
Uh-huh.
चर है चर 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 न
उसको channel में हेर्दैन न mathematics.
धेरै चर हैन अब नम्बर
Videos playlist. Central limit theorem, optics puzzle, calculus, linear algebra. Essence of calculus, essence of linear algebra. So I think linear algebra.
अब छ
ठिक हाम्रै जानुपर्छ हामीले यसमा मैले लगइन गरेँ होइन ओके
ओए तू बाध्दैन हो गुरु जन्मै नै गुरु जन्मै
continue. Okay. सुरुमा linear algebra. Mathematics for linear specialization.
Yeah, mas. कत्रो
YouTube course.
आइसकेछ
कसको होला त यो बोर्डमा बनाउनु भएको छ कसले भन्दा
हैन यहाँ फाइट छ जाउन त घुस्ती हो
कसले भन्दा
बाध्दैन हो सेसन त्यहाँ
yes
यहाँ इनी छ भन्नु
त्यही नै छ and कोर्सेसहरुमा सरी यहाँ गएर आउँछ एक्सप्लोर फिट भिडियो लिनियर अल्जेब्राको अनि क्याल्कुलस यसको हैन एसेन्स एउटा लिनियर अल्जेब्रा एउटा क्याल्कुलस पढ्न दुईटा हेर्ने अनि अलिक सो आज हेरिन्छ एसेन्स अफ लिनियर अल्जेब्रा ओके यसमा प्ले सो click
The fundamental, root of it all building block for linear algebra is the vector. So it's worth making sure that we're all on the same page about what exactly a vector is. You see, broadly speaking, there are three distinct but related ideas about vectors, which I'll call the physics student perspective, the computer science student perspective, and the mathematician's perspective. The physics student perspective is that vectors are arrows pointing in space. What defines a given vector is its length and the direction it's pointing. But as long as those two facts are the same, you can move it all around and it's still the same vector. Vectors that live in the flat plane are two-dimensional, and those sitting in broader space that you and I live in are three-dimensional. The computer science perspective is that vectors are ordered lists of numbers. For example, let's say you were doing some analytics about house prices, and the only features you cared about were square footage and price. You might model each house with a pair of numbers, the first indicating square footage and the second indicating price. Notice, the order matters here. In the lingo, you'd be modeling houses as two-dimensional vectors, where in this context, vector is pretty much just a fancy word for list, and what makes it two-dimensional is the fact that the length of that list is 2. The mathematician, on the other hand, seeks to generalize both these views, basically saying that a vector can be anything where there's a sensible notion of adding two vectors and multiplying a vector by a number, operations that I'll talk about later on in this video. The details of this view are rather abstract, and I actually think it's healthy to ignore it until the last video of this series, favoring a more concrete setting in the interim. But the reason I bring it up here is that it hints at the fact that the ideas of vector addition and multiplication by numbers will play an important role throughout linear algebra. But before I talk about those operations, let's just settle in on a specific thought to have in mind when I say the word vector. Given the geometric focus that I'm shooting for here, whenever I introduce a new topic involving vectors, I want you to first think about an arrow, and specifically, think about that arrow inside a coordinate system, like the xy plane, with its tail sitting at the origin. This is a little bit different from the physics student perspective, where vectors can freely sit anywhere they want in space. In linear algebra, it's almost always the case that your vector will be rooted at the origin. Then, once you understand a new concept in the context of arrows in space, we'll translate it over to the list of numbers point of view, which we can do by considering the coordinates of the vector. Now, while I'm sure that many of you are already familiar with this coordinate system, it's worth walking through explicitly, since this is where all of the important back and forth happens between the two perspectives of linear algebra. Focusing our attention on two dimensions for the moment, you have a horizontal line, called the x-axis, and a vertical line, called the y-axis. The place where they intersect is called the origin, which you should think of as the center of space and the root of all vectors. After choosing an arbitrary length to represent 1, you make tick marks on each axis to represent this distance. When I want to convey the idea of 2D space as a whole, which you'll see comes up a lot in these videos, I'll extend these tick marks to make midlines, but right now they'll actually get a little bit in the way. The coordinates of a vector is a pair of numbers that basically gives instructions for how to get from the tail of that vector at the origin to its tip. The first number tells you how far to walk along the x-axis, positive numbers indicating rightward motion, negative numbers indicating leftward motion, and the second number tells you how far to walk parallel to the y-axis after that, positive numbers indicating upward motion, and negative numbers indicating downward motion. To distinguish vectors from points, the convention is to write this pair of numbers vertically with square brackets around them. Every pair of numbers gives you one and only one vector, and every vector is associated with one and only one pair of numbers. What about in 3 dimensions? Well, you add a third axis, called the z-axis, which is perpendicular to both the x and y axes. And in this case, each vector is associated with an ordered triplet of numbers. The first tells you how far to move along the x-axis, the second tells you how far to move parallel to the y-axis, and the third one tells you how far to then move parallel to this new z-axis. Every triplet of numbers gives you one unique vector in space, and every vector in space gives you exactly one triplet of numbers. Alright, so back to vector addition and multiplication by numbers. After all, every topic in linear algebra is going to center around these two operations. Luckily, each one's pretty straightforward to define. Let's say we have 2 vectors, one pointing up and a little to the right, and the other one pointing right and down a bit. To add these 2 vectors, move the second one so that its tail sits at the tip of the first one. Then, if you draw a new vector from the tail of the first one to where the tip of the second one now sits, that new vector is their sum. This definition of addition, by the way, is pretty much the only time in linear algebra where we let vectors stray away from the origin. Now, why is this a reasonable thing to do? Why this definition of addition and not some other one? Well, the way I like to think about it is that each vector represents a certain movement, a step with a certain distance and direction in space. If you take a step along the first vector, then take a step in the direction and distance described by the second vector, the overall effect is just the same as if you moved along the sum of those 2 vectors to start with. You could think about this as an extension of how we think about adding numbers on a number line. One way that we teach kids to think about this, say with 2 plus 5, is to think of moving 2 steps to the right, followed by another 5 steps to the right. The overall effect is the same as if you just took 7 steps to the right. In fact, let's see how vector addition looks numerically. The first vector here has coordinates 1, 2. And the second one has coordinates 3, negative 1. When you take the vector sum using this tip-to-tail method, you can think of a 4-step path from the origin to the tip of the second vector. Walk 1 to the right, then 2 up, then 3 to the right, then 1 down. Reorganizing these steps so that you first do all of the rightward motion, then do all the vertical motion, you can read it as saying, first move 1 plus 3 to the right, then move 2 minus 1 up. So the new vector has coordinates 1 plus 3 and 2 plus negative 1. In general, vector addition in this list of numbers conception looks like matching up their terms and adding each one together. The other fundamental vector operation is multiplication by a number. Now this is best understood just by looking at a few examples. If you take the number 2 and multiply it by a given vector, it means you stretch out that vector so that it's 2 times as long as when you started. If you multiply that vector by, say, 1/3, it means you squish it down so that it's 1/3 the original length. When you multiply it by a negative number, like negative 1.8, then the vector first gets flipped around, then stretched out by that factor of 1.8. This process of stretching or squishing or sometimes reversing the direction of a vector is called scaling. And whenever you catch a number like 2 or 1/3 or negative 1.8 acting like this, scaling some vector, you call it a scalar. In fact, throughout linear algebra, one of the main things that numbers do is scale vectors. So it's common to use the word scalar pretty much interchangeably with the word number. Numerically, stretching out a vector by a factor of, say, 2 corresponds with multiplying each of its components by that factor, 2. So in the conception of vectors as lists of numbers, multiplying a given vector by a scalar means multiplying each one of those components by that scalar. You'll see in the following videos what I mean when I say that linear algebra topics tend to revolve around these two fundamental operations, vector addition and scalar multiplication. And I'll talk more in the last video about how and why the mathematician thinks only about these operations, independent and abstracted away from however you choose to represent vectors. In truth, it doesn't matter whether you think about vectors as fundamentally being arrows in space, like I'm suggesting you do, that happen to have a nice numerical representation, or fundamentally as lists of numbers that happen to have a nice geometric interpretation. The usefulness of linear algebra has less to do with either one of these views than it does with the ability to translate back and forth between them. It gives the data analyst a nice way to conceptualize many lists of numbers in a visual way, which can seriously clarify patterns in data and give a global view of what certain operations do. And on the flip side, it gives people like physicists and computer graphics programmers a language to describe space and the manipulation of space, using numbers that can be crunched and run through a computer. When I do mathy animations, for example, I start by thinking about what's actually going on in space, and then get the computer to represent things numerically, thereby figuring out where to place the pixels on the screen. And doing that usually relies on a lot of linear algebra understanding. So there are your vector basics, and in the next video, I'll start getting into some pretty neat concepts surrounding vectors, like span, bases, and linear dependence. See you then! In the last video, along with the ideas of vector addition and scalar multiplication, I described vector coordinates, where there's this back and forth between, for example, pairs of numbers and two-dimensional vectors. Now, I imagine the vector coordinates were already familiar to a lot of you, but there's another kind of interesting way to think about these coordinates, which is pretty central to linear algebra. When you have a pair of numbers that's meant to describe a vector, like 3, -2, I want you to think about each coordinate as a scalar, meaning think about how each one stretches or squishes vectors. In the xy coordinate system, there are two very special vectors. The one pointing to the right with length 1, commonly called I hat, or the unit vector in the x direction, and the one pointing straight up with length 1, commonly called j hat, or the unit vector in the y direction. Now, think of the x-coordinate of our vector as a scalar that scales I hat, stretching it by a factor of 3, and the y-coordinate as a scalar that scales j hat, flipping it and stretching it by a factor of 2. In this sense, the vector that these coordinates describe is the sum of two scaled vectors. That's a surprisingly important concept, this idea of adding together two scaled vectors. Those two vectors, I hat and j hat, have a special name, by the way. Together, they're called the basis of a coordinate system. What this means, basically, is that when you think about coordinates as scalars, the basis vectors are what those scalars actually, scale. There's also a more technical definition, but I'll get to that later. By framing our coordinate system in terms of these two special basis vectors, it raises a pretty interesting and subtle point. We could have chosen different basis vectors and gotten a completely reasonable new coordinate system. For example, take some vector pointing up and to the right, along with some other vector pointing down and to the right in some way. Take a moment to think about all the different vectors that you can get by choosing two scalars, using each one to scale one of the vectors, then adding together what you get. Which two-dimensional vectors can you reach by altering the choices of scalars? The answer is that you can reach every possible two-dimensional vector, and I think it's a good puzzle to contemplate why. A new pair of basis vectors like this still gives us a valid way to go back and forth between pairs of numbers and two-dimensional vectors, but the association is definitely different from the one that you get using the more standard basis of I hat and j hat. This is something I'll go into much more detail on later, describing the exact relationship between different coordinate systems. But for right now, I just want you to appreciate the fact that anytime we describe vectors numerically, it depends on an implicit choice of what basis vectors we're using. So anytime that you're scaling two vectors and adding them like this, it's called a linear combination of those two vectors. Where does this word linear come from? Why does this have anything to do with lines? Well, this isn't the etymology, but one way I like to think about it is that if you fix one of those scalars and let the other one change its value freely, the tip of the resulting vector draws a straight line. Now, if you let both scalars range freely and consider every possible vector that you can get, there are two things that can happen. For most pairs of vectors, you'll be able to reach every possible point in the plane. Every two-dimensional vector is within your grasp. However, in the unlucky case where your two original vectors happen to line up, the tip of the resulting vector is limited to just this single line passing through the origin. Actually, technically there's a third possibility too. Both your vectors could be zero, in which case you'd just be stuck at the origin. Here's some more terminology. The set of all possible vectors that you can reach with a linear combination of a given pair of vectors is called the span of those two vectors. So restating what we just saw in this lingo, the span of most pairs of 2D vectors is all vectors of 2D space. But when they line up, their span is all vectors whose tip sit on a certain line. Remember how I said that linear algebra revolves around vector addition and scalar multiplication? Well, the span of two vectors is basically a way of asking what are all the possible vectors you can reach using only these two fundamental operations, vector addition and scalar multiplication. This is a good time to talk about how people commonly think about vectors as points. It gets really crowded to think about a whole collection of vectors sitting on a line, and more crowded still to think about all two-dimensional vectors all at once, filling up the plane. So when dealing with collections of vectors like this, it's common to represent each one with just a point in space. The point at the tip of that vector, where, as usual, I want you thinking about that vector with its tail on the origin. That way, if you want to think about every possible vector whose tip sits on a certain line, just think about the line itself. Likewise, to think about all possible two-dimensional vectors all at once, conceptualize each one as the point where its tip sits. So, in effect, what you'll be thinking about is the infinite flat sheet of two-dimensional space itself, leaving the arrows out of it. In general, if you're thinking about a vector on its own, think of it as an arrow. And if you're dealing with a collection of vectors, it's convenient to think of them all as points. So for our span example, the span of most pairs of vectors ends up being the entire infinite sheet of two-dimensional space. But if they line up, their span is just a line. The idea of span gets a lot more interesting if we start thinking about vectors in three-dimensional space. For example, if you take two vectors in 3D space that are not pointing in the same direction, what does it mean to take their span? Well, their span is the collection of all possible linear combinations of those two vectors, meaning all possible vectors you get by scaling each of the two of them in some way and then adding them together. You can kind of imagine turning two different knobs to change the two scalars defining the linear combination, adding the scaled vectors and following the tip of the resulting vector. That tip will trace out some kind of flat sheet cutting through the origin of three-dimensional space. This flat sheet is the span of the two vectors. Or more precisely, the set of all possible vectors whose tips sit on that flat sheet is the span of your two vectors. Isn't that a beautiful mental image? So what happens if we add a third vector and consider the span of all three of those guys? A linear combination of three vectors is defined pretty much the same way as it is for two. You'll choose three different scalars, scale each of those vectors, and then add them all together. And again, the span of these vectors is the set of all possible linear combinations. Two two different things could happen here. If your third vector happens to be sitting on the span of the first two, then the span doesn't change. You're sort of trapped on that same flat sheet. In other words, adding a scaled version of that third vector to the linear combination doesn't really give you access to any new vectors. But if you just randomly choose a third vector, it's almost certainly not sitting on the span of those first two. Then, since it's pointing in a separate direction, it unlocks access to every possible three-dimensional vector. One way I like to think about this is that as you scale that new third vector, it moves around that span sheet of the first two, sweeping it through all of space. Another way to think about it is that you're making full use of the three freely changing scalars that you have at your disposal to access the full 3 dimensions of space. Now, in the case where the third vector was already sitting on the span of the first two, or the case where two vectors happen to line up, we want some terminology to describe the fact that at least one of these vectors is redundant, not adding anything to our span. Whenever this happens, where you have multiple vectors and you could remove one without reducing the span, the relevant terminology is to say that they are linearly dependent. Another way of phrasing that would be to say that one of the vectors can be expressed as a linear combination of the others, since it's already in the span of the others. On the other hand, if each vector really does add another dimension to the span, they're said to be linearly independent. So with all of that terminology, and hopefully with some good mental images to go with it, let me leave you with a puzzle before we go. The technical definition of a basis of a space is a set of linearly independent vectors that span that space. Now, given how I described a basis earlier, and given your current understanding of the words span and linearly independent, think about why this definition would make sense. In the next video, I'll get into matrices and transforming space. See you then.
Too good. Thank you for today.